Hey, this is Mr. Roark. In this video, we're going to review concepts from Unit 2. Unit 2 dealt with kinematics for accelerating objects. So we'll look at graphs again, we'll take a look at equations, try to put everything together as far as objects that are speeding up, slowing down, or changing direction. Okay, Unit 2 is all about accelerated motion. And one of the main things that students have trouble with is looking at the graphs. So let's take a look at some example graphs and talk about how they relate to each other. So I'm going to draw a position versus time graph, a velocity versus time graph, and an acceleration versus time graph. I'll just sketch these out. So for a position versus time graph, remember the slope on your position versus time graph tells you the velocity. So let's draw a line here, like this. The slope of this line is positive. The slope is also constant. It doesn't change. That means the velocity for this object is going to be positive, and it's not going to change. So on our velocity versus time graph, we would draw something that looks like this. Okay? Now, a lot of students get mixed up here because they see this thing as increasing. And yes, the position is increasing. That's what we're graphing on the vertical axis here, position. The position is increasing, but the slope of this line doesn't change. It goes the same distance every second. So the velocity has to be constant. But all the time I'll get people that say that this thing is speeding up. And actually, even more of the time, I get somebody that says something that is doing this is slowing down. Well, take a look at this. This is a position versus time graph. The position is decreasing because if we look at any two time points, here and here, we see the position goes down in a certain amount of time, but the slope, the actual slantedness of the line doesn't change. That means this thing has to have a constant velocity. And the only thing that's going to change on our velocity versus time graph is that it's going to have a negative velocity because the slope is negative. So this thing is just going backwards. It's moving in the opposite direction, but the slope doesn't change, so the velocity can't change. Now, if we take a look at this, if the velocity doesn't change, automatically we should know the acceleration is zero. But another way we can take a look at it, on our velocity versus time graph, here's our line on our velocity versus time graph right here. We can see that has a flat or zero slope. Just like the slope on the position versus time graph tells us the velocity, the slope on a velocity versus time graph tells us the acceleration. So here, zero slope gives us zero acceleration. But that is what we were looking at in Unit 1. In Unit 2, we were looking at where we actually had acceleration. So let's maybe take a look at this backwards. What if we had a constant positive acceleration? So we had a line that looks something like that. Well, it kind of depends on where you start. If the object starts from rest, it starts with a velocity of zero, that means a constant positive acceleration is going to speed it up. And so the velocity will increase towards the positive direction. It's getting faster and faster and faster and faster and faster. But what if it didn't start at zero? What would happen if it started and already had a positive velocity? That would mean the starting velocity is not zero, but it's up here somewhere. It's up here on the vertical axis. So all that would mean is that the object is speeding up, but it didn't start from zero. It's still getting faster and faster. And one way we can look at that is it has a positive acceleration, and it also has a positive starting velocity. So when the acceleration and the velocity have the same sign, the thing is going to speed up. It's going to get faster and faster and faster. However, what would it look like if the thing would start with not a positive velocity, but a negative velocity? What if it started down here? We can't change the slope of this line. I mean, we already said it has a positive acceleration. We drew this line. all we're doing is changing the starting point of the velocity. So if the velocity starts negative, then it's going to start down here. In this region, right here, this object is actually slowing down. Now that might be hard to think about because it has a positive slope. But look at where the zero velocity is. It's on this line right here. It's on the x-axis. So this object is actually getting, to start off, the velocity is getting closer and closer to zero. So this thing is slowing down to begin with, and then it hits a zero velocity, and it speeds up in the other direction. So another way to look at it, going back to what we just talked about, the acceleration here is positive, but it started with a negative velocity. Because the acceleration and the velocity have different signs, this object is going to initially slow down. The velocity was in the negative direction. It has an opposite acceleration, so that's going to take away from the velocity until it's taken all the velocity away, and it ends up at zero. And then if the acceleration continues, then it can speed up again. Okay? Let's go back to our original situation. And of course, if the acceleration were negative, well, all that's going to change is the slope of this line. That would make it slant that way instead. It'd have a negative slope for that negative acceleration. And so here would be an object that is speeding up in the negative direction. Here would be an object that is speeding up in the negative direction, but it started with a negative velocity. Here would be an object that slows down to begin with, because again, the velocity is getting lower and lower. It's getting closer to zero, and so the velocity actually decreasing, and then it will speed up in the negative direction. And again, we see that because we start with a negative velocity, or acceleration here, excuse me, and a positive velocity, and those two things have opposite signs, so we get this initial slowing down period. Okay, but, oops. Let's take a look at the position versus time values, because that's where people usually have the trouble. So we've got positive acceleration. We're going to say this thing starts from a velocity of zero, and it increases. These things are interconnected by the slope. The velocity right here comes from the slope on the position versus time graph. You got to be a little bit careful about what you're doing. The velocity here starts at zero and increases. That tells us that on a position versus time graph, the slope has to start at zero and increase. And a lot of people will go, okay, I need a line that starts at zero and increases. Well, this shows a line that does that, but we need the slope to do that. Look at the slope here. The slope of this does not change. The slantedness doesn't change. We have to show an object that starts with zero velocity. It gets faster and faster and faster. It has to gain more and more position as time goes on. The slope has to start at zero, meaning it has to start with a flat line, and the slope of it needs to increase. So this shows an object that is actually speeding up. The velocity increases and increases and increases as it goes away from position zero. And we see that from the curve of the line. Anytime you have an object that is accelerating, you should have a line that is curving. What if we had, say, a negative slope here, though, because we have a negative acceleration? Well, in this case, the only difference here is the object is still speeding up because it started at zero, but it's speeding up in the negative direction. That would mean the slope needs to increase in the negative direction. So if we started from this point right here, it's still starting with a flat line, but it has to increase in the negative direction. So the slope has to increase and get steeper and steeper and steeper, but towards the negative end. So these right here, this is an object that is speeding up in the positive direction. This one is speeding up in the negative direction. Now let's take a look at what happens if an object is slowing down. Let's get rid of those. So let's say this object started out with a positive velocity, and it's going to slow down and get closer and closer to zero. The acceleration is negative here. But because it started with a positive velocity, that means it had to start with some slope. So that means the slope has to start positive and go to 0, just like the velocity is doing. This thing should get closer to a flat line. So we need to start with a positive slope and curve towards 0. This would show an object that is slowing down, moving in the positive direction. What about if it was slowing down, moving in the negative direction? We'd have to have positive acceleration, and we'd have to have an object that starts negative. So it starts with a negative velocity and goes towards 0. So that's what our velocity versus time graph would look like. Well, in this case, we have a negative velocity. The velocity goes towards 0. That means we have to start with a negative slope, and the slope goes towards 0. So here, the slope has to start negative. It has to be pointed downward, and it's going to curve towards a 0 slope. It has to flatten out. Anywhere the object has a velocity of 0, you should have a flat line. So here it curves the other way and flattens out. So if we put these back up here, this was an object that sped up in the negative direction. This is an object that sped up in the positive direction. You can see how these things are kind of related. Both of these objects are moving in the positive direction, but one is speeding up because the line is getting steeper. One, blue, is slowing down because it's getting flatter. And we see the exact same thing in the negative direction. This one is speeding up, the line is getting steeper. This one is slowing down, the line is getting flatter. So another thing you should be able to do in Unit 2 is to do ball and ramp problems. So remember, this is where we have a ball and ramp set up. The ball is going to be rolling around the ramp, along the ramp. There's going to be places where it speeds up, places where it slows down, places where it may stay at a constant speed. We should be able to draw position, velocity, and acceleration versus time graphs for any type of ball and ramp setup that we have. So let's take a look at the one that I've got here. Now, in my opinion, the velocity versus time graph is the easiest to do. It's the most, it's the one that's easiest to think about. Now, one thing we need to know to make a velocity versus time graph is what our starting velocity is. So, in these qualitative setups like this, the velocity is either going to start at 0 or it's not. And it tells us right here the velocity does not start at 0. That makes sense because the way our ball and ramp set up here is, if this thing started with 0 velocity, it would not go anywhere. That'd be pretty boring. So we know this thing is moving to begin with, and we're going to assume that in all these ball and ramp setups that it has enough velocity to make it through the entire course. So velocity does not start at 0. So that means I cannot start it on the x-axis on my velocity versus time graph. Now, we need to decide what direction it's moving in. Well, we see we've got a negative sign right here and a positive sign right here. So this thing is moving towards the positive end of the number line. That means it's moving in the positive direction the whole time. So my velocity here has to start somewhere on the vertical axis on the positive end of the number line. So let's say it starts, I mean, it's got a little bit arbitrary because these are qualitative graphs, but it's going to start somewhere up there. Conceptually, I know this ball is going to slow down as it rolls up the ramp. My velocity is going to decrease. So I can show that on. My velocity decreases. Now I don't want to have it go all the way to 0 though. If it goes all the way to 0, that would mean it stops somewhere on here. We're assuming it has enough velocity to go all the way through the ramp. So it has to back off and stop slowing down at some point when it goes over this curve. Because I know when it goes over this hill right here, then it's going to speed up again. So the velocity is going to increase back and get faster and faster. And then on this flat portion, we know this thing should stay at constant speed because we're assuming in all these ball and ramp setups that friction and air resistance is negligible. And so the velocity should stay the same the whole time. So here we have a velocity time graph that shows an object that is moving in the positive direction, slowing down, and then speeding up, and then going a constant velocity. And again, your velocity versus time graph should have a shape that is similar to that of the shape of the ramp. It's not a great idea just to memorize that because depending on whether the ball is moving in the positive or negative direction, the shape could be switched around the x-axis. If you draw a velocity versus time graph and it looks absolutely nothing like the ramp, then you need to back up and think about it again. Now, if you can draw a velocity versus time graph, really the acceleration versus time graph should be simple, because the way these things are put together, from position versus time graph to velocity versus time graph, and then from velocity versus time graph to acceleration versus time graph, they're all interconnected through the slopes. So the slope of position versus time graph tells you the velocity versus time graph. The slope of the velocity versus time graph tells you position versus time graph. Now, if we had actual numbers here, we could actually calculate slopes, but we don't. We've got qualitative graphs. So all we can really tell is the slope positive, negative, or zero. So in this case right here, the first part, we have a negative slope. It's moving in the positive direction, but slowing down. So we have a negative acceleration, and the acceleration is going to be constant. Then in this case right here, we have a positive slope. This object is speeding up. So it's going to jump to a positive acceleration. Remember, we're going to assume that these things just jump between accelerations. So we're going to draw a dotted line just to show that those are interconnected. And then this part right here, the object is not speeding up or slowing down. So you know the acceleration has to be zero. And we can see the slope of that part of the graph is zero. So the acceleration jumps down to zero. So we've got our acceleration versus time graph, our velocity versus time graph. Now all we need is our position versus time graph. To draw a position versus time graph, the first thing you need to start off with is the starting position and the ending position. So it tells us right here that the starting position is zero. So we know on our graph we have to start right here. Because it's moving in the positive direction, it's going to end up somewhere on the positive part of the position versus time graph, somewhere up here. But of course, time has to go on, so we'll draw a dot right there. So I know where it starts. I know where it ends up. The only thing I have to be concerned with now is what the lines look like in between those things. Anywhere the velocity changes, or if you think about it, anywhere there's acceleration, so in this first third of the graph right here, we draw a dotted line, we know the position versus time graph has to curve. Because anytime there's a changing velocity, the slope has to change on the position versus time graph. Because again, these things are connected through the slope. If the slope on a position versus time graph tells me the velocity, that means the velocity will tell me what the slope is doing. We can work that backwards. So here, the velocity starts positive and decreases. That means my slope has to start positive and decrease. Well, a positive slope starts out like this. But it has to decrease. That means that has to curve closer to a flat line. So it's going to curve like this a little bit. We're not going to make it completely flat because that would mean the object's sitting still and it doesn't stop. But it curves like that to begin with. The next part is just the opposite. It's going to speed up. It increases back towards the positive. That means my slope increases back towards the positive. So it kind of goes back to where it was to begin with. It curves back that way. And then for this last part here, the slope is at zero. There's no acceleration. That means the slope on my position versus time graph should not change at all. It should stay constant. And so a constant slope is just a straight line. So I should draw a nice straight line, which can be a little bit hard to do. But this thing should curve towards flat, curve away from flat, and then stay the same. Let's take a look at the equations that we deal with in Unit 2. So in Unit 2, we have basically 3 equations. And the first one I'm going to look at is this one. It's actually the mathematical definition of acceleration. Acceleration is equal to the change in velocity divided by the time. Now you can use this to find the acceleration of an object if you know the velocity it started at, the velocity it ended up at, and how much time went by. An important point here, because when we find change in velocity, we always take final minus initial. That means when the object loses velocity or slows down, the acceleration should end up negative. If the velocity increases and it gets faster, the velocity should end up positive. This is also directly related to the slope on a velocity versus time graph. We've got a velocity versus time graph here, and we find the slope of a line on there. all we're finding is the change in velocity on the vertical axis and the change in time on the horizontal axis. And then when we find the slope, we're just taking that rise and dividing by the run, which is the acceleration. So you see just from this mathematical definition why the slope on a velocity versus time graph is equal to the acceleration. Another important equation is this nice big long one, which we call the position equation. We use this all the time. So it says that the position at any point in time is equal to an object's initial position plus its initial velocity times its time plus 1/2 times the acceleration times the time squared. And there's a lot of people that end up leaving out that time squared part, but it's important. So the point of this equation is it says, okay, if I want to know exactly where an object is, what do I need to know? I need to know where it started. That's important, because if I don't know where it started, then there's no way to know where it's going to end up. For most cases, we can call the starting point 0, because when we set up an equation, we can say, okay, here's my number line. The origin of my number line is going to be exactly where the object starts. It makes the math a lot easier, and we can just call the initial position 0. But it is important to know that. This next part right here, velocity times time, this basically tells us how far the object moves because of a constant velocity. So the object starts off at a velocity of, say, 30 meters per second. Because it's moving to begin with, it's going to move a certain distance based on that initial velocity and how long the object is moving for. This final part right here tells us how much further the object moves or less far it moves if it's a negative acceleration because it's speeding up or slowing down. So things that are going to speed up are going to move further than they would have if they were going at constant velocity. Things that slow down and have a negative acceleration are not going to move quite as far. We can see if you put in a negative acceleration here, it's actually going to take some distance away from that constant velocity. But basically, this tells us how much extra you gain or how much you lose because of your speeding up or slowing down. And this last part tells you how far you're going to go because of your constant velocity. And of course, if the acceleration here ends up being 0, then this whole part cancels out because 0 times all of that is 0. And you're left with just this part right here, which tells us how far an object goes if it's going a constant velocity. And that makes sense because if your acceleration is 0, then your velocity is constant. The final equation we're going to talk about is this one right here. This is the velocity equation. It says if I want to know how fast an object is going at any point in time, I need to know the starting velocity, so how fast it was going when the clock started. I need to know how fast it accelerated at, how much it sped up or slowed down, and I need to know how long it actually did that speeding up or slowing down. So we call this the velocity equation, and this right here is only going to be 0 if the object starts out from rest. Now there's a lot of objects that do start out from rest, but not all of them. And too often we get people that are doing this calculation and they just automatically cross that out and say that's 0. But that's only true if the object actually starts from rest. If it's moving to begin with, you need to fill that in. That's the initial or starting velocity. Technically based on the unit, it's actually the velocity at time 0. But that's the point. That's how fast it's moving when you start analyzing the subject. And we can see here, based on that starting velocity, if our acceleration is positive, then when we multiply by the time, we're going to add these together and we'll get a bigger and bigger velocity as time goes on, so the thing will be speeding up. If the acceleration is negative, then when we multiply by the time, we're going to get a negative part, and it's going to add that velocity and actually take away from it. It'll be slowing and slowing down. So these two equations here, the position equation and the velocity equation, are very important kinematic equations. And they can be used to figure out a lot of different things about objects that are moving. And as we'll see in Unit 3, we're going to connect all of those different things using the acceleration, which we'll figure out from the force diagrams.